Tonight, we're going to talk about what happens inside a black hole, past the event horizon, past the point where space and time, as you understand them, stop working the way they should, into the region that sits behind the most extreme boundary in the known universe, where the gravitational field is so total, so absolute, that not light, not radiation, nothing that carries information of any kind has ever come back out. The interior of a black hole is sealed from the outside universe by definition. Everything that crosses the threshold stays there. And what happens on the other side of that threshold, to space, to time, to matter, to information, is one of the deepest questions in all of science. By the end of tonight, you're going to understand why nothing that crosses that boundary ever comes back, and what happens to it when it doesn't. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something you think you already understand. Gravity. You've lived with gravity your entire life. It pulls you toward the floor. It holds the moon in its orbit. It keeps Earth circling the sun. The intuitive picture most people carry is of gravity as a force, an invisible pull reaching out across empty space between objects that have mass. That picture is useful, and it's the framework that Isaac Newton gave us in 1687. Newton's law of universal gravitation stated that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It's elegant. It worked extraordinarily well. Newton's gravity let us predict the motions of planets to high precision, explain ocean tides, calculate the trajectories of cannonballs and rockets, and eventually plan the precise courses of interplanetary spacecraft. For more than 200 years after Newton, it was among the most successful scientific theories ever produced. But it was wrong. Not completely wrong. Not wrong in its predictions within the range where it was tested, but wrong at a deeper level. Newton's gravity described what gravity does. It didn't describe what gravity actually is. And the difference between those two things matters enormously for everything we're going to discuss. The deeper answer came from Albert Einstein. In 1915, after nearly a decade of extraordinarily difficult intellectual work, Einstein published his general theory of relativity. What he discovered fundamentally changed our understanding of space, time, and gravity. Gravity, Einstein showed, is not a force reaching across space. It's a consequence of the curvature of space-time. Space-time is the four-dimensional fabric that combines the three dimensions of space with the one dimension of time into a single, unified structure. Before Einstein, physicists thought of space and time as separate, fixed, unchanging background stages on which events played out. General relativity says something completely different. Space and time are dynamic. They can warp, curve, stretch, and compress. Mass and energy warp the fabric of space-time around them. Objects then follow the straightest possible paths through that curved space-time. Those paths are what we call gravitational trajectories. You're not being pulled toward the ground by a force Earth is exerting on you. Earth is curving space-time around it, and you're following the straightest path available in that curved geometry. That path leads toward the ground. The curvature of space-time, not a force, is what gravity actually is. This is not a subtle, semantic distinction. It has profound consequences for how we understand extreme gravitational environments like black holes. Because a black hole isn't just an object with very strong gravitational force. It's a region where space-time itself has been curved so severely that all possible paths through it, every direction you could possibly travel, point inward toward the center. There is no path through curved space-time inside a black hole that leads outward. The geometry itself forbids it. Most people picture the event horizon as a wall, a surface, something you'd crash into. It's none of those things. The event horizon is not a physical surface. Nothing you could touch, feel, sense by any direct local measurement or detect by any instrument as you crossed it. It's a mathematical boundary in space-time. It has a precise definition in the language of general relativity. The event horizon is the outer boundary of the region of space-time from which no future-directed causal curve can escape to infinity. Let's unpack that. A future-directed causal curve is any path through space-time that moves forward in time and always travels at or slower than the speed of light. Any actual physical object, any signal, any particle with mass, any photon, follows a future-directed causal curve. Nothing can travel faster than light. So the event horizon is the boundary from which no physical object, no signal, no light, nothing that obeys the laws of physics can ever reach the outside universe. Stand just outside the event horizon. Fire a laser outward. The laser beam will escape and eventually reach a distant observer. Stand just inside the event horizon. Fire a laser in any direction, straight out, at an angle, even almost tangentially. In every case, the laser beam will be curved back toward the singularity by the geometry of space-time. It will never reach a distant observer. The event horizon is the last location from which outward travel is geometrically possible. The Schwarzschild radius gives the size of this boundary for a non-rotating black hole. It was derived by Carl Schwarzschild in November of 1915, within weeks of Einstein's publication of General Relativity. Schwarzschild was a German physicist and astronomer who at the time was serving as an artillery officer on the Russian front during World War I. He solved Einstein's famously difficult field equations exactly, producing the first known exact solution. He sent his derivation to Einstein in a letter from the Eastern Front. Einstein was astonished by the speed and elegance of the solution. He presented Schwarzschild's work to the Prussian Academy of Sciences. Schwarzschild himself died the following year, in May of 1916, from a skin disease he contracted while serving in the war. He never knew that his solution would become the foundational description of black holes, objects that most physicists of his era didn't believe could actually exist. The Schwarzschild radius is given by 2 times Newton's gravitational constant, times the mass, divided by the speed of light squared. Numerically, for an object of 1 solar mass, this works out to about 3 kilometers. So, a black hole of 1 solar mass has an event horizon radius of 3 kilometers. The full event horizon is a sphere 6 kilometers in diameter. The Sun is 1.4 million kilometers in diameter. You'd need to compress it by a factor of more than 200,000 to create a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. Squeeze all of Earth's mass into a sphere about 18 millimeters across, and it's a black hole. For a billion-ton asteroid, the Schwarzschild radius is smaller than a proton. These numbers give you a visceral sense of how extreme the compression required for black hole formation really is. It doesn't happen from gentle compression. It requires the catastrophic collapse of an entire stellar core under gravity, so intense that no known force of nature can stop it. There is something deeply strange about how black holes appear to distant observers that gets at the heart of relativity. Time itself behaves differently near a black hole. This isn't a metaphor. It isn't a perceptual illusion. It's a physical reality confirmed by experiments. General relativity predicts that time runs slower in stronger gravitational fields. This is called gravitational time dilation. At sea level on Earth, in Earth's gravitational field, time runs slightly slower than at altitude, where gravity is weaker. The effect is tiny at everyday scales. But the GPS satellites orbiting Earth at an altitude of about 20,000 kilometers experience weaker gravity than the surface. Time runs faster for them by about 45 microseconds per day due to gravity, partially offset by a smaller effect from their orbital speed. The net difference is about 38 microseconds per day. If GPS satellites didn't constantly correct for this relativistic effect, positioning errors would accumulate at a rate of about 11 kilometers every day. The entire system would become useless within hours. The correction is real. Time dilation is real. Near a black hole, this effect becomes extreme. An object falling toward the event horizon appears, from the perspective of a distant observer, to slow down as it approaches. This is not because the object is actually slowing down. It's because the light the object emits is fighting harder and harder against the gravitational pull to escape. Each photon, climbing away from near the event horizon, loses energy to gravity. That energy comes from the photon's frequency, its color. The photon becomes redder. Its wavelength stretches. The time between successive wave crests grows longer. This means that a clock near the event horizon appears, to a distant observer, to tick more and more slowly. An infalling clock appears to slow, its ticking rate approaching zero as it approaches the horizon. From the distant observer's perspective, the infalling object asymptotically approaches the event horizon. It gets closer and closer. It fades and reddens. But it never quite reaches the horizon. The light from the final approach takes infinite time to reach a distant observer. So from outside, you never see anything cross. This is consistent with observations of matter falling into black holes. Gas and dust, spiraling into black holes, fades and reddens in exactly this way. The mathematics is confirmed. But from the reference frame of the falling object itself, the story is completely different. This is the central strangeness of general relativity. The falling observer does cross the event horizon, in a finite amount of their own proper time. For a stellar mass black hole, this happens in a fraction of a second. For a supermassive black hole, it might take minutes or hours of subjective time from when they begin their freefall far outside. Both accounts, the distant observer who never sees the crossing and the falling observer who crosses, are equally valid. There is no privileged reference frame. Neither account is the correct one. Both are correct from their respective frames. This is what relativity means. Different observers can give completely different accounts of the same physical situation, and both accounts are self-consistent and physically real. The crossing happens and doesn't happen depending on who you ask. From the perspective of someone falling freely into a large enough black hole, the experience at the event horizon itself is profoundly unremarkable. There's nothing to feel. No physical indicator. No visible marker. No alarm. No wall. If you were wearing a spacesuit with all its instruments, you would detect nothing unusual at the moment of crossing. Your local environment would obey all the usual laws of physics. Your heartbeat would continue at its normal pace. Your instruments would all read normally. The crossing happens, and you don't know it happened. This is a consequence of one of the foundations of general relativity, the equivalence principle. Any freely falling observer in a sufficiently small region of space-time and for a sufficiently short time experiences physics indistinguishable from flat space-time with no gravity. A person falling freely in a gravitational field is locally equivalent to a person floating in the absence of any gravitational field. An observer in a falling elevator cannot determine by any local experiment whether they're falling toward Earth or drifting in deep space far from any mass. At the event horizon of a large enough black hole, the equivalence principle applies in full. The freely falling observer sees nothing locally unusual. The crucial qualification is large enough. Because the event horizon is only locally equivalent to flat space-time, there's still gravity, still the curvature of space-time, still the tidal forces that arise from the fact that gravity varies in strength and direction across extended objects. For a small black hole, the event horizon is close to the singularity. The tidal forces, the difference in gravitational acceleration between one end of an object and the other, are enormous at the event horizon. For a stellar mass black hole with a Schwarzschild radius of a few kilometers, the gradient of the gravitational field over a distance of a human body is large enough to produce enormous tidal forces. These forces stretch you in the direction toward the singularity and compress you perpendicular to that direction. The stretching dominates. You're pulled longer and thinner, and longer, and thinner. This process has a technical term in the scientific literature: spaghettification. This is genuinely what physicists call it, and it describes exactly what happens. For a stellar mass black hole, spaghettification occurs well before you reach the event horizon. You don't make it to the horizon intact. The tidal forces end you while you're still outside. But for a supermassive black hole, the geometry is entirely different. The Milky Way's central black hole, Sagittarius A, has a mass of about 4 million times the Sun. Its event horizon has a radius of about 12 million kilometers. That's about 8% of the distance from Earth to the Sun. At a distance of 12 million kilometers from the center, the tidal forces, the differential gravity across the length of a human body, are actually comparable to what you feel standing on Earth's surface. Perfectly survivable. The event horizon of Sagittarius A can be crossed in free fall with no local indication. Nothing would register as unusual. It's only later, as you fall deeper toward the singularity, that tidal forces grow to dangerous levels. By then, you're already inside. The point of no return is behind you. And for black holes more massive than Sagittarius A, the crossing is even gentler. The black hole at the center of the galaxy Messier 87, with a mass of about 6.5 billion solar masses. It has an event horizon so large and a central singularity so far from the horizon that you could spend days inside it before reaching dangerous tidal forces. The firewall, as we'll discuss, might change this picture. But according to classical general relativity, the crossing of a supermassive event horizon is the most anticlimactic moment in what would otherwise be a remarkable journey. Now we can follow the journey inward. You've crossed the event horizon of a supermassive black hole. Nothing dramatic happened. Your instruments read normally. You're continuing in freefall. But something has changed profoundly in the geometry of space-time around you. Inside the event horizon, the mathematics of the Schwarzschild solution reveals something extraordinary. The radial coordinate, the direction pointing toward the center, has exchanged character with the time coordinate. Outside the event horizon, the time coordinate has a special property. It flows in one direction only. You cannot go backward in time. You can move in any direction in space, but time only goes forward. Inside the event horizon, the radial coordinate acquires this property. It points in one direction only, toward the singularity. You cannot move away from the singularity, not because it's pulling you like a drain, but because the geometry of space-time is such that away from the singularity is not a direction that exists inside the event horizon. It's geometrically not a possible direction. This is the correct way to think about why escape is impossible. It's not that the force is too strong. It's that the direction you'd need to travel doesn't exist inside the event horizon. The singularity is in your future, the way tomorrow is in your future. You can try to delay reaching it. You can fire rockets and extend the time before you arrive. Different trajectories lead to different amounts of proper time before you reach the singularity. Firing rockets radially outward is the worst strategy. Counterintuitively, remaining in free fall, not fighting, extends your proper time inside the black hole the longest. This is because proper time is maximized along geodesics, the freefall paths, and minimized by deviation from freefall. The universe has a dark sense of humor here. The peaceful approach, just falling, gives you the most time. Fighting gains you nothing, and it costs you proper time. But even the maximum possible proper time inside the event horizon is finite. The singularity is coming regardless. For a solar mass black hole, the proper time from crossing the event horizon to reaching the singularity is on the order of microseconds. For Sagittarius A, with its 4 million solar mass event horizon, the maximum proper time inside is around 20 seconds. For Messier 87's 6.5 billion solar mass black hole, the maximum is roughly hours. For Ton 618, with its 66 billion solar masses, it could be days. But in every case, the end comes. The geometry ensures it. What would you actually see and experience during the fall? The visual environment inside a black hole is described by the mathematics, and it's deeply strange. Looking outward, away from the center and back in the direction of the event horizon, you would see the outside universe compressed into a bright circle. That circle contains all the light that entered the black hole. Not just the light that was there when you crossed. Light that enters after you does so as well. If you cross the event horizon, the outside universe is still visible from inside, but compressed into a smaller and smaller region of your visual field as you fall deeper. Looking toward the singularity, there's nothing. The singularity emits no radiation in the classical picture. It's the end of space-time, not an object within space-time. The interior of a black hole is not a bright, glowing place. It's dark. One bright compressed circle in one direction, containing the entire outside universe. Darkness in all other directions. And as you fall deeper, the circle shrinks. The outside universe becomes a smaller and smaller spot. The tidal forces grow. The direction toward the singularity is stretching you. The perpendicular direction is compressing you. For a large enough black hole, this is survivable for a while. but the forces grow as the inverse cube of the distance from the singularity. They don't grow gradually. They accelerate toward infinity as you approach the center. Whatever quantum gravity does to the singularity, whatever physical reality replaces the mathematical infinity, it happens in the final moments of the fall. And whatever it is the most extreme physical process that exists in the universe. There is a complication to the picture of a falling observer that becomes important when we think about what an observer might see near the event horizon. It's not a subtle theoretical point. It's an active area of debate that reaches to the foundations of both quantum mechanics and general relativity. Hawking radiation. Stephen Hawking showed in 1974 that black holes radiate. They're not perfectly black. They emit thermal radiation with a temperature inversely proportional to their mass. This result came from applying quantum field theory in the curved spacetime of a black hole. The derivation is technically involved, but the physical picture has an accessible version. In quantum mechanics, the vacuum, empty space, is not truly empty. It seethes with what are called quantum fluctuations. Virtual particle-antiparticle pairs spontaneously appear from the vacuum energy, exist for a time, constrained by the uncertainty principle, and then annihilate. They borrow energy from the vacuum, exist briefly, and return the energy. They can't be directly detected because they vanish too quickly. But they have measurable effects on physical systems. The Casimir effect, the measurable force between two closely spaced metal plates in vacuum, is one consequence. The anomalous magnetic moment of the electron is another. Virtual particles are not a metaphor. Their effects are measured and match theory to extraordinary precision. At the event horizon of a black hole, something can happen to these virtual pairs that doesn't happen in ordinary space. A pair appears right at the horizon. One member falls inside. The other is just outside. Before they can annihilate each other, they're separated by the horizon. The one inside is swept toward the singularity. The one outside has no partner to annihilate with. It becomes a real particle, carrying real energy, and it escapes. From the perspective of energy conservation, the energy for this real particle comes from somewhere. That somewhere is the black hole's own mass energy. The black hole loses a tiny amount of mass with each such event. The escaping radiation is thermal. It has a temperature. For a solar mass black hole, the Hawking temperature is about 60 billionths of a Kelvin. That's far below the temperature of the cosmic microwave background, the glow of radiation left over from the Big Bang that permeates all of space at about 2.7 Kelvin. So a solar mass black hole would actually absorb more energy from its surroundings than it radiates through Hawking radiation. It would grow, not shrink. Only after the universe has expanded and cooled sufficiently, far in the future, would solar mass black holes begin to net evaporate. But the principle is real. Black holes have a temperature. Black holes radiate. Black holes are not permanent. They will, eventually, evaporate completely. The timescale for a solar mass black hole to evaporate is incomprehensibly long, about 2 × 10⁻�67 years. The current age of the universe is about 14 billion years, which is roughly 10⁻10 years. The evaporation timescale for a solar mass black hole is longer than the current age of the universe by a factor of more than 10⁻57. No useful comparison puts that in perspective. It is simply a very large number. But the end will come. And for smaller black holes, the evaporation is faster. A hypothetical black hole with the mass of a mountain would evaporate in a timescale comparable to the current age of the universe. A black hole with the mass of a large boulder would evaporate in seconds. And in the final moments of any black hole's evaporation, as the temperature climbs to extraordinary values and the evaporation accelerates, the last burst of radiation is energetic. The final evaporation of a black hole is not gentle. It's a burst, a flash, and then nothing. Where the black hole was, there's empty space. And whatever fell in is, apparently, gone. Or is it? This question, simple to state and profound in its implications, is the information paradox. In quantum mechanics, information is conserved. This isn't an assumption or a convenience. It's a fundamental consequence of how quantum mechanics works. The equations of quantum mechanics are unitary. They evolve quantum states in ways that, in principle, allow the past to be reconstructed from the present and the future to be predicted from the past. No information is ever truly destroyed. A burned book doesn't destroy information. It scrambles and disperses it into smoke and ash and radiation, but in principle, with perfect knowledge of all the particles and their states, you could reconstruct the book. The same principle applies to everything in quantum mechanics. Everything that ever happened leaves an indelible mark on the quantum state of the universe. Now, consider a black hole. A star of a specific composition, with a specific internal structure, a specific rotation rate, specific quantum states for all its constituent particles, collapses to form a black hole. More matter falls in over time. The black hole sits there. And then, slowly, it evaporates through Hawking radiation. The Hawking radiation appears thermal. It has a temperature, a characteristic spectrum, but no information about what fell in. A black hole that formed from a collapsed star looks identical, from the outside, to a black hole of the same mass that formed from collapsed hydrogen gas or antimatter, or old spaceship components. The Hawking radiation from both would look identical. No information about the infalling material appears to be encoded in the radiation. And when the black hole has completely evaporated, all that remains is a cloud of thermal radiation. Random, featureless, informationally empty. The information about what fell in appears to have been destroyed. This violates unitarity. It violates one of the core principles of quantum mechanics. Stephen Hawking originally argued that this violation was real. That information was genuinely lost in black hole evaporation. That the formation and evaporation of a black hole represents a true, fundamental failure of unitarity. Most physicists found this deeply unacceptable. The debate became one of the most contentious in theoretical physics. At stake was nothing less than the validity of quantum mechanics itself, which underpins our entire understanding of chemistry, electronics, nuclear physics, and essentially all of modern technology. In 2004, at a conference in Dublin, Hawking publicly conceded that he now believed information was not lost, that it was somehow encoded in the Hawking radiation. He paid off a bet he had made with another physicist. But how information could be encoded in radiation that appears perfectly thermal and random remained deeply mysterious. The information paradox is not resolved. It remains one of the central open questions in theoretical physics. The first major attempt to resolve the paradox without giving up either quantum mechanics or general relativity was called black hole complementarity. It was developed primarily by Leonard Susskind, together with Gerard Hooft, in the early 1990s. The proposal starts from a careful accounting of what different observers actually see. A distant observer watching a quantum state fall into a black hole sees something specific. The quantum state approaches the event horizon. It slows, reddens, fades. It appears to smear across the horizon surface. As the black hole evaporates over an enormous span of time, the information in that smeared state is somehow encoded in the Hawking radiation that escapes. From the outside observer's perspective, the information never enters the black hole. It stays on the surface and eventually leaves. An observer, falling with the infalling quantum state, experiences something completely different. They cross the event horizon without incident. The quantum state passes inside intact, carrying its information. The information enters the black hole interior. These two descriptions appear to flatly contradict each other. The information both stays outside and falls inside. Susskind argued there's no contradiction, because no single observer can ever verify both accounts simultaneously. To confirm that the information escaped in Hawking radiation, you need to collect the radiation for an astronomical span of time, process it, and extract the information. But by the time you've done that, the black hole has evaporated. There's no interior left. You can't go in and check. If you do go in before the evaporation is complete, you can't send the information back out. The universe never has to reconcile the two accounts. It never has to admit a contradiction. Complementarity says the universe is protected from paradox by the impossibility of any single observer experiencing both descriptions. It's philosophically uncomfortable. It feels like the universe is hiding something. Many physicists found it clever but insufficient. In 2012, a paper by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully showed that complementarity, as stated, leads to a genuine internal contradiction. The authors are collectively referred to by their initials, AMPS. Their argument was precise and disturbing. Quantum mechanics requires that Hawking radiation carries away the information from the black hole. For this to work, the late radiation, emitted toward the end of the black hole's life, must be entangled with the early radiation, emitted at the beginning. This entanglement is what encodes the information. But quantum mechanics also requires, through a standard analysis of what a freely falling observer experiences at the horizon, that the late radiation be entangled with the modes inside the black hole. And here is the problem. Quantum entanglement is monogamous. A quantum system can be fully entangled with only one other system. If the late radiation is fully entangled with the early radiation, as required for information preservation, it cannot also be entangled with the interior modes. But if it's not entangled with the interior modes, something breaks at the event horizon. Quantum field theory predicts that the vacuum, empty space, near the event horizon should look smooth and featureless to a freely falling observer. This is the equivalence principle in quantum language. The smoothness of the vacuum across the event horizon requires specific entanglement between the modes inside and outside. If you break that entanglement, the vacuum is no longer smooth. It's energetic. Violently energetic. A wall of radiation at the horizon. A firewall. The AMPS paper concluded that either information is truly lost, violating quantum mechanics, or The event horizon is surrounded by a wall of Planck-scale energy that destroys everything, crossing it, violating the equivalence principle and general relativity. Either quantum mechanics is wrong, or general relativity is wrong. Both in a fundamental way. The paper caused a sensation in the physics community. It was argued about intensely at conferences and in papers. Many physicists felt something must be wrong with the AMPS argument. General relativity and the equivalence principle have been tested to extraordinary precision. The idea that an astronaut falling into a black hole hits an invisible firewall at the horizon rather than crossing it smoothly felt deeply wrong. But the argument was tight, and no one quickly found the error. The firewall debate is ongoing. A satisfying resolution has not been found. The question of what actually happens at the event horizon, whether it's a gentle crossing or an instant end, depends on physics we don't fully understand. The most ambitious proposed resolution of the firewall paradox came from Juan Maldacena and Leonard Susskind. In a paper published in 2013, they proposed a connection between two ideas that had seemed entirely unrelated. One is the concept of a wormhole, or Einstein-Rosen bridge. In 1935, Einstein and Nathan Rosen showed that the maximally extended Schwarzschild solution to Einstein's equations contains two exterior regions, connected by a bridge through the interior. Not a hole in space that you can travel through. A geometric connection between two separate spacetimes. The two regions can't communicate. Nothing can travel through the Einstein-Rosen bridge. But geometrically, the connection is there in the mathematics. Also, in 1935, Einstein collaborated with Boris Podolsky and Nathan Rosen on a different paper, pointing out a striking prediction of quantum mechanics. Two particles can be entangled in such a way that measuring the quantum state of one instantaneously determines the quantum state of the other, regardless of the distance between them. This is quantum entanglement. Einstein found it deeply uncomfortable. He called it spooky action at a distance and used it to argue that quantum mechanics must be incomplete. He was wrong about that. Quantum entanglement is real and has been confirmed by countless experiments. But the connection between entanglement and his other 1935 paper, the Einstein-Rosen bridge, went unnoticed for almost 80 years. Maldacena and Susskind propose that they are the same thing. Two maximally entangled quantum systems are connected by a wormhole. Quantum entanglement is a wormhole. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs. ER equals EPR. If this is correct, then the Hawking radiation outside a black hole and the interior of the black hole are connected by a network of quantum wormholes created by the entanglement between them. The information doesn't escape through the event horizon the way a particle escapes. It doesn't tunnel through in the conventional sense. It's encoded in the geometric structure of space-time itself, created by the quantum entanglement between inside and outside. The firewall paradox might be dissolved because the apparent contradiction between the outside and inside descriptions is resolved by recognizing that they're connected by a quantum space-time structure that the original analysis didn't account for. This is beautiful. It's also speculative, and it points toward something even deeper. If entanglement creates geometric connections, then space-time geometry might emerge from quantum entanglement. Space itself might be made of entanglement. The fabric of reality, at the most fundamental level, might be quantum information. These are among the deepest ideas currently being explored in theoretical physics. They're not confirmed. They're not even fully formulated. But they point toward a picture of reality more profound than anything we've had before. The holographic principle deserves careful attention because it's central to the modern understanding of black holes and information. In 1993, the Dutch physicist Gerard Hooft proposed an idea that initially seemed almost absurd. He argued that the information content of any region of space is not proportional to the volume of that region. It's proportional to the area of the surface enclosing it. The maximum amount of information that can be stored in a region of space is determined not by how much volume is inside, but by how much area is on the outside. This is deeply counterintuitive. We're used to thinking of information as stored in volume. Books store information in their pages, which fill a volume. Hard drives store information in the volume of their magnetic material. But Hooft argued that gravity places a fundamental limit on how much information can occupy a volume of space. Try to pack in more information than the holographic bound allows, and you'll create a black hole. And the information content of the resulting black hole is encoded on its event horizon. 2 dimensions, not 3. The surface, not the volume. For a black hole, this is the Bekenstein-Hawking entropy formula. Jacob Bekenstein discovered in 1972 that black holes must have entropy. Entropy is a measure of the number of microscopic states that are consistent with the macroscopic properties you observe. It's a measure of information. Bekenstein realized that if black holes had no entropy, you could violate the second law of thermodynamics by throwing entropy into a black hole and making it disappear. To avoid this, black holes must have entropy, and the entropy must be enormous. Hawking calculated it precisely. The entropy of a black hole is proportional to the area of its event horizon in units of the Planck area. The Planck length is about 1.6 times 10 to the negative 35 meters. The Planck area is the square of that. Each Planck area on the event horizon contributes 1 unit of entropy. 1 bit of information. The event horizon of a solar mass black hole, a sphere with a radius of 3 kilometers, has an area of roughly 113 square kilometers, divided into Planck areas. That's an astronomically large number of bits, about 10 to the power of 77. All of that information, all of it, is encoded on the 2-dimensional surface of the event horizon. The 3-dimensional interior of the black hole is, in some sense, a projection of the information on the boundary. Like a hologram, which encodes a 3-dimensional image on a 2-dimensional surface, the interior of a black hole is described by the information on its horizon. This led Leonard Susskind to develop the holographic principle more broadly. He proposed that the entire universe might be holographic, that the physics of the interior of any region is fully encoded on the boundary surrounding it. The 3-dimensional space we inhabit might be, in a precise mathematical sense, a projection of information encoded on a 2-dimensional surface at the edge of the observable universe. This is not a claim that the universe is a simulation or an illusion. It's a claim about how information is organized in the universe. The most concrete mathematical realization came from Juan Maldacena in 1997. Maldecena's discovery, now known as the anti-de Sitter over conformal field theory correspondence, or ADS, CFT for short, is one of the most important results in theoretical physics of the past 30 years. Maldacena showed that string theory in a specific curved spacetime, called anti-de Sitter space, is exactly equivalent to a quantum field theory that lives on the boundary of that spacetime. Exactly equivalent means every physical question in the bulk spacetime, including questions involving black holes, event horizons, and singularities, has a precise translation into a question in the boundary quantum field theory. The two theories are dual descriptions of the same physical reality. What makes this extraordinary is that the boundary quantum field theory has no gravity. It's a conventional quantum mechanical system. It obeys all the usual quantum mechanical rules, including unitarity. Information is preserved in the boundary theory. Full stop. And since the two theories are equivalent, information must be preserved in the bulk theory as well, including inside black holes. This proves, at least in the anti-de Sitter spacetime, that information is not lost when black holes form and evaporate. The black hole in the bulk corresponds to a certain thermal state in the boundary theory. The Hawking radiation in the bulk corresponds to the slow thermalization and eventual re-radiation of information in the boundary theory. The information is preserved. Our universe is not anti-de Sitter space. Our universe has a positive cosmological constant, not a negative one. The ADS-CFT correspondence doesn't directly apply. But the result is widely taken as strong evidence that information is preserved in real black holes too. The mechanism by which it happens, the precise quantum gravitational processes that encode information in Hawking radiation, is what remains to be worked out. And the Page curve calculation from 2019 gave us the first concrete evidence that the mechanism works in the expected way. The Page curve, named for Don Page, who calculated its expected shape in 1993, describes what happens to the entanglement entropy of Hawking radiation over the lifetime of a black hole. If information is lost, the entanglement entropy of the radiation just keeps growing as the black hole evaporates. The radiation is maximally entangled with nothing, just random and thermal. If information is preserved, something different happens. At first, as the black hole starts evaporating, the radiation is entangled with the interior of the black hole. The entropy grows. But there's a transition called the Page time, which occurs roughly halfway through the black hole's evaporation. After the Page time, as the remaining black hole shrinks, the Hawking radiation becomes entangled with previously emitted radiation, not with the interior. The entropy of the radiation starts to decrease. By the time the black hole has completely evaporated, the entropy returns to zero. The radiation is in a pure state. All the information has been returned. For decades, no one knew how to derive the Page curve from the gravity side, the side involving the actual black hole. The standard Hawking calculation just gave monotonically increasing entropy. No Page curve. In 2019, Jeffrey Pennington at Stanford and Ahmed Al-Mehri, together with colleagues at the Institute for Advanced Study, independently showed how to derive the Page curve using a new understanding of quantum extremal surfaces and a technique from holography, including the contributions of what they called island regions inside the black hole, regions that are gravitationally connected to the outside in the quantum gravity sense. They were able to reproduce the Page curve from a first principles gravity calculation. The entropy rises, peaks at the Page time, and falls back to zero. It was a breakthrough. Not a complete solution, but the strongest evidence yet that black hole evaporation preserves information, and that the holographic principle correctly describes the quantum gravity of black holes. The singularity and the information paradox are not completely resolved. But the mathematical tools for resolving them exist, and people are using them. The rotating black hole, described by Roy Kerr's 1963 solution, introduces a rich inner structure not present in the non-rotating case. All real black holes rotate. Every star that collapsed to form a black hole was already rotating, and the collapse amplified that rotation. A rotating black hole is not spherically symmetric. It has a preferred axis, the rotation axis. Space-time outside a rotating black hole is dragged around the rotation axis. This is called frame dragging, or the Lentz-Thirring effect. The black hole's rotation pulls space-time with it, like a rotating ball embedded in honey pulls the honey around it. This effect has been measured around Earth. The Gravity Probe B satellite, launched in 2004, confirmed that Earth's rotation drags space-time by exactly the tiny amount predicted by general relativity. Around a rapidly rotating black hole, frame dragging is extreme. There's a region outside the event horizon of a Kerr black hole called the ergosphere. Inside the ergosphere, space-time is dragged so fast that nothing can remain stationary with respect to distant stars. Even traveling at the speed of light in the direction opposite the black hole's rotation, you're still carried along. You can still escape from the ergosphere, because the outer boundary of the ergosphere is outside the event horizon. But you cannot stand still. Interestingly, the ergosphere allows energy to be extracted from the black hole's rotation. A process called the Penrose process, proposed by Roger Penrose in 1971, allows this. If an object enters the ergosphere and splits into two pieces, with one piece falling into the black hole on a specific trajectory, the other piece can escape with more kinetic energy than the original object had. The extra energy comes from the rotational energy of the black hole. The black hole loses a tiny amount of angular momentum and mass. Accumulated over time, this process can drain the rotation of a black hole. The relativistic jets launched from actively accreting supermassive black holes, those enormous structures stretching millions of light years, are likely powered by a magnetic version of this process, the Blandford-Znaick mechanism, which extracts energy from the black hole's rotation through magnetic fields threading the ergosphere. The largest structures in the universe, powered by the smallest regions in the universe. Inside the Kerr black hole, the structure differs fundamentally from the Schwarzschild case. There are two event horizons, an outer event horizon and an inner event horizon, called the Cauchy horizon. The region between them is the part of space-time where outward escape is impossible, the same as inside the Schwarzschild event horizon. But inside the inner Cauchy horizon, the structure changes again. The singularity in the Kerr case is not a point. It's a ring. A one-dimensional circle with zero thickness and zero width, but non-zero radius, lying in the equatorial plane of the black hole's rotation. At the ring singularity, the curvature becomes infinite. The mathematics breaks down. But unlike the Schwarzschild point singularity, which lies in the future of every infalling trajectory, the Kerr ring singularity is off to the side. Certain trajectories passing through the Cauchy horizon can avoid the ring singularity entirely. They can pass through the center of the ring. And when the Kerr solution is extended maximally, as mathematicians do to find the full extent of a spacetime, what appears beyond the ring singularity is another universe. Not another region of our universe. A separate space-time, connected to ours through the interior of the black hole. And beyond that, possibly, yet another. In an infinite chain, the mathematics is clear. But does it describe physical reality? Almost certainly not. For the Kerr solution as written, the Cauchy horizon inside a rotating black hole is unstable. This was understood through the work of several physicists in the 1970s and 80s. Matter and radiation falling into the black hole accumulate at the inner horizon. From the perspective of something crossing the inner horizon, an infinite amount of infalling material arrives in a finite time. The energy density at the inner horizon diverges. A singularity forms there. Not the ring, singularity of the idealized Kerr solution. A null singularity at the inner horizon itself. This was first understood by the physicists Werner Israel and Eric Poisson, who studied what they called mass inflation at the inner horizon. The upshot is that the wormhole structures and alternate universes of the idealized Kerr solution almost certainly don't exist in real rotating black holes. They're mathematical artifacts of an idealized solution. Real black holes have a singularity at or near the inner horizon, not a passage to another universe. But the physics of what exactly happens at the inner horizon of a real rotating black hole, accounting for quantum effects and the full dynamics of infalling radiation, is not fully worked out. It remains an active area of research. Among the most important large-scale structures associated with black holes are the jets that launch from actively accreting systems. When matter falls toward a black hole, it doesn't fall straight in. It has angular momentum, the rotational momentum from its original motion. Angular momentum must be conserved. So infalling material spirals inward, forming an accretion disk. The disk is an extraordinarily energetic place. Friction, magnetic fields, and viscosity within the disk heat the gas to extreme temperatures. In the inner accretion disk around a stellar mass black hole, temperatures reach tens of millions of Kelvin. Around a supermassive black hole, the temperatures in the corona above the disk can reach billions of Kelvin. The disk radiates intensely across the electromagnetic spectrum. This is why actively accreting black holes are the brightest sources in the universe. Within the disk, magnetic fields are amplified by the differential rotation. Faster rotation in the inner regions, slower in the outer regions, wraps and strengthens magnetic field lines. This creates a powerful, structured magnetic field threading through the inner disk. Near the poles of a rapidly spinning black hole, these magnetic fields, combined with the frame dragging of the ergosphere, launch jets of relativistic plasma along the rotation axis. The Blandford-Znaeck process extracts energy directly from the black hole's rotation. The jets can reach velocities of 99% of the speed of light, or more. They extend outward, sometimes for millions of light years. They slam into the surrounding intergalactic medium. They create enormous radio lobes, giant structures of magnetized plasma that can dwarf the host galaxy. The jet from Messier 87's central black hole is visible and extends for about 5,000 light-years. It was one of the first jets ever photographed, discovered by the American astronomer Heber Curtis in 1918, though its nature wasn't understood for decades. All of this happens just outside the event horizon. The jets originate in the ergosphere and inner accretion disk, regions above the event horizon. Nothing that goes past the event horizon contributes to the jet. Everything past that line, the physics of the interior, the singularity, whatever quantum gravity describes at the center, is sealed. The spectacular structures we observe are what happens at the threshold. The inside remains hidden. Gravitational wave astronomy has given us an entirely new way to observe black holes and test general relativity in the strong field regime. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses a brilliantly simple but extraordinarily precise technique. A laser beam is split and sent down two perpendicular arms, each 4 kilometers long. The beams reflect off mirrors at the ends and return to a detector. Normally, the beams travel exactly equal distances and recombine to cancel each other out. If a gravitational wave passes, it stretches one arm and simultaneously squeezes the other. The path lengths become unequal. The beams no longer perfectly cancel. A signal is detected. The sensitivity required is almost incomprehensible. A gravitational wave from a black hole merger 1 billion light-years away causes LIGO's arms to change length by about 1,000th of the diameter of a proton. 1,000th of a proton diameter. For reference, a proton is about 10 to the negative 15 meters in diameter. LIGO detects movements of about 10 to the negative 18 meters. Smaller than any scale that has any meaning in chemistry or conventional physics. The first detection, on September 14, 2015, was 2 black holes, one of about 36 solar masses and one of about 29 solar masses, merging to form a black hole of about 62 solar masses. 3 solar masses of material were converted directly into gravitational wave energy in a fraction of a second. The energy output in that brief moment exceeded the luminosity of all the stars in the observable universe combined. The signal, after traveling roughly 1.3 billion light-years, arrived at LIGO as a rising chirp, lasting less than a second. The signal matched the predictions of general relativity, calculated from the masses and spins of the merging black holes to extraordinary precision. The ringdown phase, the period after merger when the newly formed black hole oscillates and radiates away its excess energy, matched exactly the expected pattern for the Kerr metric. The merged black hole rings like a bell at its natural frequency. The frequency and the rate at which the ringing decays depend on the mass and spin. By measuring these, we test whether the resulting object is consistent with the Kerr solution. So far, every merger we've detected is consistent with general relativity, not approximately. Within the measurement precision, exactly. Since the first detection, LIGO and its European partner Virgo have detected dozens of mergers. Black hole binaries, neutron star binaries, mixed systems. Each one a brief signal from a catastrophe that happened hundreds of millions or billions of light-years away, encoded in the stretching of space-time itself. The ongoing observations are providing a census of black hole masses and spins. The mass distribution of black holes is telling us about stellar evolution, stellar populations, and the history of galaxy formation. Gravitational wave astronomy has become a mature observational science, and its reach, its precision, is a direct test of general relativity in regimes that were completely inaccessible before. The most massive known black hole is TON 618, a quasar at a redshift corresponding to a distance of about 10.4 billion light-years. Its estimated mass is about 66 billion solar masses. Its Schwarzschild radius is about 1,200 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. So, TON 618's event horizon encompasses a region more than 1,000 times the distance from Earth to the Sun in radius. The orbit of Pluto is about 40 astronomical units from the Sun. The event horizon of TON 618 is roughly 30 times larger than the orbit of Pluto. The tidal forces at the event horizon of this black hole are utterly negligible. If you cross the event horizon of TON 618 in freefall, the tidal forces at the moment of crossing would be less than the tidal forces you experience standing on Earth's surface. Completely survivable. The singularity, using the maximum proper time trajectory, would take roughly years of subjective time to reach. You would have years inside the largest known black hole in the universe. Years during which you could observe, measure, think, and none of your measurements could ever reach the outside world. Everything that happens inside TON 618's event horizon is permanently sealed from the universe we can observe. All of the information you might gather would be sealed with it. The universe's largest known prison. Invisible, impenetrable. Governed by physics we don't fully understand. Black holes don't wander through space seeking things to swallow. This is worth stating explicitly because the popular image often implies a gravitational vacuum cleaner. A black hole of any given mass has exactly the same gravitational influence at a distance as any other object of the same mass. If the Sun were somehow replaced by a black hole of equal mass, 1 solar mass, with an event horizon of 3 kilometers in radius, every planet in the solar system would continue orbiting exactly as before. Earth would orbit at the same distance, with the same period. Nothing about the gravitational field beyond the event horizon would change. You'd be very cold and very dark, but gravitationally the solar system would be unaffected. The event horizon of a solar mass black hole is 3 kilometers in radius. Earth is 150 million kilometers from the Sun. Earth would have to wander to within 3 kilometers of the singularity to pass the event horizon. The probability of that happening is essentially zero. Most black holes in the galaxy are doing nothing dramatic. They're sitting quietly in interstellar space or orbiting slowly at the centers of star clusters, occasionally having a passing star or gas cloud come close enough to contribute some infalling material. Stellar mass black holes in our galaxy number perhaps tens of millions. They're scattered through the disk and halo. Most have no nearby material to accrete. They're completely dark, invisible. You could pass within light years of one and never know it was there. It's only when a black hole has material to accrete, a companion star it's stealing gas from, a dense cloud of infalling matter, a major galaxy merger bringing fresh material to the center, that they light up. And even then, the radiation comes from outside the event horizon. The infalling material heats up as it spirals in before it crosses the point of no return. The event horizon itself remains perfectly dark. That's what it means to be a black hole. Nothing escapes, including light, including information, including any evidence of what's inside. The universe contains 3 established categories of black holes based on mass. Stellar mass black holes, with masses from a few to about 100 solar masses, form from the collapse of massive stars. They're the most common type. Supermassive black holes, with masses from millions to tens of billions of solar masses, sit at the centers of large galaxies. They're thought to grow through a combination of mergers and gas accretion, and a middle category, intermediate mass black holes, with masses between about 100 and 1,000,000 solar masses, have been sought for decades and are now being confirmed with observations, including gravitational wave detections of unusually massive merger products. A fourth class, primordial black holes, may have formed in the early universe from density fluctuations in the first fraction of a second after the Big Bang. They remain speculative. If they exist and are in the right mass range, they could constitute some portion of dark matter. Searches for their signatures are ongoing. The supermassive black holes at galactic centers are among the most intensely studied objects in astronomy. We've known about Sagittarius A, the black hole at the center of the Milky Way, for decades. But the evidence for its existence has accumulated slowly. The key evidence came from tracking the orbits of stars in the galactic center. The galactic center is surrounded by a cluster of stars called the stars, or Sagittarius cluster. These stars are in tight orbits around a compact, dark, massive central object. The star, S2, has an orbital period of about 16 years. Its orbit has been tracked for decades by astronomers at the European Southern Observatory and at the Keck Observatory. The shape of its orbit, an ellipse with the focus at the position of Sagittarius A, matches the predictions for an orbit around an object of about 4 million solar masses, concentrated in a region smaller than our solar system. Nothing other than a black hole of that mass fits the data. In 2020, the Nobel Prize in Physics was awarded in part to Reinhard Genzel and Andrea Ghez for their decades of work, tracking these stars and establishing the existence of Sagittarius A. The Nobel Committee called it the discovery of a supermassive compact object at the center of our galaxy, a diplomatic phrasing that everyone understood to mean a black hole. The following year, the Event Horizon Telescope collaboration, the same team that imaged Messier 87's black hole in 2019, released an image of Sagittarius A. It was technically more challenging than Messier 87. Sagittarius A is much closer, only 26,000 light-years away, but its environment is turbulent. Gas and dust between us and the galactic center distort and scatter the radio waves. The black hole also varies quickly on human timescales because it's smaller. The image showed a ring of light surrounding a central dark region, similar to Messier 87, different in detail, but unmistakably the same kind of object. Two direct images of two different black holes, both matching the predictions of general relativity, both showing the photon ring, both hiding their interiors behind the dark shadow. The question of what happens inside is where everything converges. We've established what the exterior looks like. We understand the ergosphere, the event horizon, the accretion disk. We understand the Hawking radiation, the information paradox, the holographic principle. We have strong mathematical evidence that information is preserved. We have ongoing debate about what exactly happens at the horizon. The firewall remains unresolved. The singularity is where our best theory breaks down. Two candidate theories of quantum gravity, string theory and loop quantum gravity, each propose a resolution of the singularity. In string theory, the fundamental constituents of reality are not point particles. They're one-dimensional vibrating strings. Different modes of vibration correspond to different particles. The mathematics of string theory naturally incorporates gravity as a consequence of the vibrational modes of closed strings. String theory requires extra spatial dimensions beyond the three we experience, typically 6 or 7 extra dimensions curled up at scales too small to detect with current instruments. At the energies where string effects become important, which is near the Planck scale, point-like singularities are smeared out. Strings have a finite size. You can't compress a string to a point. The singularity of the black hole interior is replaced by a region of extreme but finite string-scale physics. What exactly happens there, from the perspective of an infalling observer, depends on the string coupling and the specific geometry. But the infinite density of the classical singularity is gone. Loop quantum gravity takes a different approach. It doesn't modify the matter content, adding strings. It quantizes space-time itself. In loop quantum gravity, space is not a smooth, continuous fabric. At the Planck scale, it's granular, made of discrete quanta of volume and area, called spin networks. The geometry of space-time is quantized. You can't subdivide space below the Planck length, any more than you can divide an electric charge below the fundamental charge of an electron. In loop quantum cosmology, which applies these ideas to the universe itself, the Big Bang singularity is replaced by a quantum bounce. The universe didn't begin from a point. It contracted to a minimum size determined by the Planck scale and then bounced. Applied to black holes, loop quantum gravity predicts that the singularity is replaced by a similar quantum bounce. Infalling matter reaches Planck density, bounces, and the outgoing matter creates what would look from outside like a white hole, an object from which matter is expelled rather than absorbed. The evaporation problem is resolved because the matter eventually comes back out in a form so scrambled as to be unrecognizable but informationally complete. The timescale for this bounce, as seen from outside, could be extremely long due to gravitational time dilation. Possibly much longer than the Hawking evaporation time. These are theoretical proposals. Neither string theory nor loop quantum gravity has been confirmed by experiment. The energies required to test their distinctive predictions are far beyond current or planned particle accelerators. But both are serious, mathematically consistent attempts to describe the quantum nature of space-time, and both make predictions about the black hole interior that differ from the classical general relativistic picture. When we finally have a confirmed quantum theory of gravity, the singularity will be resolved. What it will say is the most important open question in physics. The history of physics gives reason for confidence that the resolution will be revolutionary. Every time physics has encountered a singularity, an infinity, in the equations where the theory breaks down, a deeper theory has come along that resolved it and revealed a new layer of reality. Classical electromagnetism predicted that a free electron orbiting an atomic nucleus would spiral inward and radiate away all its energy in a fraction of a second. Every atom would collapse instantly. This singularity was resolved by quantum mechanics. The electron doesn't spiral in because quantum mechanics forbids continuous energy loss below the ground state. The resolution revealed the entire quantum world, the foundation of chemistry, materials, science, and modern technology. The prediction by classical thermodynamics that a hot object radiates infinite energy at high frequencies, the ultraviolet catastrophe, was also resolved by quantum mechanics. Planck's discovery that energy comes in discrete chunks, not a continuous flow, fixed the problem and launched quantum theory. The singularity at the center of a black hole will be resolved by quantum gravity. What the resolution will reveal, what new layer of reality it will expose, is not something we can predict from within our current framework. But the history of physics says it will be profound. It will change what we understand about space, time, matter, energy, and information. Perhaps fundamentally. Perhaps the granular structure of space-time at the Planck scale will be as revolutionary for 22nd century physics as quantum mechanics was for 20th century physics. We don't know. But the problem is sharp. The tools are developing, and the smartest people in physics are working on it. The next time you see an image of a black hole, or hear about a gravitational wave detection, or read a headline about a distant quasar powered by a supermassive black hole eating its way through a galaxy, you'll know something that most people don't. You'll know that the images show us the edges. The accretion disk, the gravitational lensing, the jets. Spectacular. Real. Measurable. Extraordinary. But the shadow at the center of that famous image, the dark region where light can't come from, that's where the real story is. That's where all the information that ever fell in is sealed forever from the outside. That's where general relativity quietly admits it doesn't have the final word. That's where quantum mechanics and gravity, the two great pillars of modern physics that have refused to speak a common language for a century, are forced to meet. Whatever they agree on, when they finally do, it will change everything we think we understand about the universe at its most fundamental level. The universe built these things. It scattered them through every galaxy. It put one at the center of the Milky Way. It left the equations that describe them lying in a letter from the Eastern Front in 1915. And then it drew a line around the most interesting part. Everything on this side you can measure, photograph, deduce, verify. Everything past this line, figure it out another way. We're working on it. One equation at a time. One observation at a time. One idea at a time. The inside of a black hole is the universe's most honest question. It's the place where everything we know points towards something we don't. Where the best theory of gravity ever produced raises its hand quietly and says that something else is happening here, and it doesn't know what. There's something almost elegant about that. The object that captures everything and releases nothing also captures the limit of our understanding and releases nothing from there either. But physics has never stopped at a limit. It has always found a way through. And on the other side of this one is probably the deepest understanding of reality that humanity has ever reached. We know where the darkness begins. We're learning what it's made of. The gravitational influence of Sagittarius A extends far beyond the immediate neighborhood of its event horizon. The galactic center is a crowded, violent, extraordinary place. Within the inner parsec of the galaxy, a parsec being about 3.26 light-years, the density of stars and gas is millions of times higher than in the solar neighborhood. Hot, young, blue stars orbit close to Sagittarius A, in tight, fast orbits. Gas and dust clouds have been observed falling toward the black hole and creating brief flares of X-ray and infrared emission as they do. In 2019, astronomers observed an unprecedented flare from Sagittarius A, a burst of near-infrared emission about 75 times brighter than normal. It lasted for a few hours. Its origin is not fully understood. It may have been caused by a clump of material falling into the accretion flow or by a magnetic reconnection event in the plasma near the event horizon. The event horizon of Sagittarius A is about 12 million kilometers in radius. That's about 1/13 of the Earth-Sun distance. From our position, 26,000 light-years away, the angular size of this event horizon is about 50 microarcseconds. An arcsecond is 1/3600th of a degree. 50 microarcseconds is 50 millionths of an arcsecond. That's the apparent size of a grapefruit on the Moon. Imaging something that's small from Earth requires a telescope as large as Earth, which is exactly what the Event Horizon Telescope constructed virtually by linking radio observatories around the world. The Event Horizon Telescope is not a single telescope. It's a planet-sized array of synchronized radio dishes using a technique called very long baseline interferometry. In very long baseline interferometry, multiple telescopes observe the same object simultaneously. The signals from each telescope are recorded with precise timestamps and later combined computationally. The resulting resolution is equivalent to a single telescope with a diameter equal to the greatest distance between any two telescopes in the array. For the Event Horizon Telescope, that maximum baseline is essentially the diameter of Earth. The dishes that contributed to the 2019 image of Messier 87 and the 2022 image of Sagittarius A included telescopes in Hawaii, Chile, Mexico, Arizona, Spain, and at the South Pole in Antarctica. The South Pole Telescope is particularly important. It provides a baseline with the northern observatories of nearly Earth's full diameter. Each telescope records terabytes of data per night, using atomic clocks accurate to a trillionth of a second to timestamp every observation. The hard drives from the South Pole Telescope had to be physically flown out on cargo planes during the Antarctic summer. Because the data volumes are too large to transmit over any available network connection. Combining all the data computationally creates the virtual Earth-sized telescope. The image reconstruction is an inverse problem. You have measurements of certain Fourier components of the image, and you need to reconstruct the image itself. Multiple algorithms were used independently, and the teams compared results before seeing each other's outputs. The consistency of the results gave confidence in the final image. The bright ring in the images of both Messier 87 and Sagittarius A comes from multiple physical contributions. Some of it is light that traveled directly from the accretion disk to the telescope. Some is light that traveled around the black hole once before escaping. Some traveled twice. Each orbit leaves a slightly brighter contribution at a slightly smaller angular radius. The multiple rings are present in the data, but not fully resolved in the images. Future improvements to the array will resolve them. The dark shadow at the center of each image is the absence of light. It's not perfectly dark in the images because of the finite resolution of the telescope and the foreground emission from the accretion disk. But it's much darker than the surrounding ring. It marks the region where light cannot escape, where the event horizon is, where everything past that threshold is permanently hidden. The behavior of the accretion disk around a black hole is governed by some of the most extreme physics in the universe. Matter can't fall straight into a black hole easily because it carries angular momentum. A particle orbiting a black hole has angular momentum from its orbital motion. To fall in, it has to lose that angular momentum. In the disk, viscosity and turbulence, driven primarily by magnetic instabilities, transfer angular momentum outward while allowing matter to spiral slowly inward. The key instability is the magnetorotational instability, discovered by Evgeny Velikov in 1959 and independently rediscovered and shown to be relevant to accretion by Stephen Balbus and John Hawley in 1991. The magnetorotational instability works as follows. Imagine two fluid elements in the disk connected by a magnetic field line. The inner one orbits faster than the outer one. The magnetic field line acts like a spring connecting them. The outer element gets pulled ahead slightly by the spring. That increases its angular momentum. More angular momentum causes it to move to a larger radius where it orbits more slowly. The inner element gets pulled back. Less angular momentum causes it to fall to a smaller radius where it orbits faster. The coupling destabilizes the differential rotation of the disk. The result is vigorous turbulence, which efficiently transports angular momentum outward and allows matter to spiral inward. This is what makes accretion disks work. The magnetorotational instability has been confirmed in laboratory experiments with liquid metal and demonstrated in numerical simulations of remarkable precision. It's one of the best understood aspects of black hole accretion. The inner edge of the accretion disk is bounded by what's called the innermost stable circular orbit. For a non-rotating black hole, this sits at 3 times the Schwarzschild radius, or 3 times further from the center than the event horizon. Inside this radius, circular orbits become unstable. A particle perturbed slightly inward will spiral into the black hole rather than returning to a circular orbit. For a maximally rotating Kerr black hole, the innermost stable circular orbit moves much closer to the event horizon in the prograde direction. This increases the efficiency with which infalling matter converts its gravitational energy to radiation. A maximally spinning black hole can convert up to about 42% of the rest mass energy of infalling matter to radiation before it crosses the event horizon. This extraordinary efficiency is why quasars can be so luminous. The infalling matter radiates away nearly half its rest mass energy before disappearing. It's the most efficient, large-scale energy conversion process in the universe. Nuclear fusion in stars, for comparison, converts about 0.7% of rest mass energy. The efficiency difference is a factor of about 60. Black hole accretion is 60 times more efficient than stellar nuclear burning. The enormous jets launched from accreting black holes are one of the most dramatic consequences of that accretion. A jet from an active galactic nucleus starts in the innermost region of the accretion disk and the ergosphere of the black hole. Strong magnetic fields thread the accretion disk. The differential rotation of the disk winds up these magnetic field lines. The wound-up fields exert a pressure that can launch plasma along the magnetic field lines, shooting it away from the disk in both directions along the rotation axis. The Blandford-Znayak mechanism adds to this by extracting energy directly from the rotation of the black hole through the threading magnetic field. The jets are collimated over enormous distances by the magnetic field itself. They can remain coherent for millions of light years. The jet from the radio galaxy Centaurus A, the nearest active galaxy to Earth at about 13 million light-years distance, extends for more than 13,000 light-years. The jet from Messier, 87, extends for about 5,000 light-years before it terminates in a bright knot where it slams into the intergalactic medium. These jets heat and displace the gas in galaxy clusters, the largest structures of hot gas in the universe, filling the space between the thousands of galaxies in a cluster, are shaped and stirred by jets from central supermassive black holes. The energy from those jets prevents the gas from cooling and forming new stars. A supermassive black hole, through its jets, regulates how many stars form in the surrounding galaxy. The feedback between black holes and their host galaxies is one of the important processes controlling galaxy evolution on cosmic scales. The event horizon is the engine. The jets are the exhaust. And the scale of that exhaust, millions of light years, powered by energy extracted from a region smaller than our solar system, gives some sense of what the event horizon represents physically. The most concentrated source of energy in the universe, releasing its power just before the point where release becomes impossible. There's a way of thinking about the information paradox that cuts to the heart of what physics actually is. Physics is built on the idea that the laws of nature are complete and consistent, that there is a mathematical description of reality that is correct and doesn't contradict itself. The information paradox threatens this. If information is truly lost in black hole evaporation, then the laws of quantum mechanics are not complete. There's a process, black hole formation and evaporation, that takes a pure quantum state, a state with definite quantum information, and converts it to a mixed state, a state with no definite quantum information. This cannot happen in any quantum mechanical theory. Pure states evolve to pure states. Information is never destroyed. Unitarity is not optional. It's the foundation. But if information isn't lost, then something must encode the information in the Hawking radiation. And the only structure available is the quantum state of the radiation itself, which means the radiation cannot be purely thermal. It must carry subtle correlations. Correlations that, if you could measure them all with perfect precision, would allow you to reconstruct everything that ever fell into the black hole. The correlations are present, but almost undetectably small. Accessing them requires measuring the quantum state of every particle in the Hawking radiation with perfect accuracy. Then, waiting for the entire black hole to evaporate. Then, performing quantum computations of extraordinary complexity. The information is there in principle. It's essentially inaccessible in practice. But the distinction between in principle and in practice is what separates physics from engineering. The laws of physics don't care about what's practical. They say, the information is there. What they don't yet say clearly enough is where, exactly, and how it got from inside the event horizon to outside. That's what ADSES, CFT, and quantum extremal surfaces and the island formula are beginning to work out. The path to the answer is clearer than it was 5 years ago. Much clearer than 10 years ago. The problem is hard, and the tools are still developing. But the direction is better understood. There is one more aspect of black holes that rarely appears in popular discussions, but is crucial for a complete picture. Black holes are not static. Even an isolated black hole, with nothing falling in, changes over time. Through Hawking radiation, a black hole slowly loses mass and shrinks. The temperature rises as the mass falls. For a stellar mass black hole, the evaporation time is so long that the change over any human-relevant timescale is negligible. But in the deep future of the universe, when all the stars have burned out and the last white dwarfs have cooled, the black holes will remain. They will be the last significant structures in an otherwise near-empty universe. And slowly, over those incomprehensible spans of time, even the largest will shrink. The supermassive black holes will take longer. The largest black hole known, TON 618, with its 66 billion solar masses, will take about 10 to the power of 95 years to evaporate. The current age of the universe is about 10 to the power of 10 years. The evaporation of ton 618 is in a future so remote that all other physical processes in the universe will have long since completed. All stars burned out. All stellar remnants cooled. All protons, if proton decay occurs, decayed. The universe will be empty except for black holes. And then, one by one, over periods of time that have no analogy in current human experience, the black holes will evaporate. Each one ending in a burst of Hawking radiation. Intense for the small ones, extended for the large ones, but ultimately a burst. And then empty space. No more information available from outside. No more photographs possible. All the information that was ever inside black holes, if information is preserved, encoded in the correlations of Hawking radiation, spread across a cold, dark, empty universe. There, somewhere, encoded in quantum correlations between particles that no one is around to observe, is the entire history of everything that ever fell into every black hole. The information exists. It's just spread across the universe in a form so scrambled that reconstructing it would require a quantum computer the size of the universe and longer than the age of the universe to operate. The universe is, in a sense, its own memory. It keeps everything, just not always in a form that's useful. The Event Horizon Telescope is not finished working. New dishes are being added. Space-based components are planned that would extend the baseline beyond Earth's diameter. Higher frequency observations will provide higher resolution. Future images of Sagittarius A and Messier 87 will show finer structure. The multiple photon rings, each produced by light that has orbited the black hole a different number of times, may become resolvable. If they are, we can test general relativity in the photon sphere in new ways. The shape of the shadow, the exact profile of the photon ring, and the dynamics of the accretion disk all encode information about the black hole's mass and spin, and about the geometry of space-time near the event horizon. Precision measurements of these quantities test whether the object is truly a Kerr black hole, as general relativity predicts, or whether there are deviations that might point to new physics. So far, everything is consistent with Kerr. Future observations will tighten those constraints, or potentially find deviations. Gravitational wave observatories are also being upgraded. LIGO and Virgo have gone through multiple observation runs with increasing sensitivity. LIGO is currently undergoing improvements that will extend its range. The planned Einstein telescope, a next-generation gravitational wave observatory in Europe, will have 10-kilometer arms in an underground triangular configuration. It will be sensitive to gravitational waves from black hole mergers across most of the observable universe. The Laser Interferometer Space Antenna, LISA, is a planned space-based gravitational wave observatory that will be sensitive to lower frequencies than ground-based detectors. It will detect the mergers of supermassive black holes in the centers of merging galaxies, events that happened billions of light years away and billions of years ago. LISA will observe the inspiral of compact objects into supermassive black holes, called extreme mass ratio inspirals, which trace the space-time geometry of the supermassive black hole with extraordinary precision over thousands of orbits. These observations will test general relativity in the strong field regime with a precision that current instruments can't match. Pulsar timing arrays provide yet another window. Networks of precisely timed pulsars are sensitive to gravitational waves at even lower frequencies than LISA. These are the frequencies produced by supermassive black hole binaries in the final stages of in-spiral before merger. In 2023, several pulsar timing array collaborations announced evidence for a gravitational wave background. A cosmic hum of gravitational waves from supermassive black hole mergers throughout the universe. The signal was consistent with the expected background from billions of supermassive black hole binaries in distant galaxies. The era of gravitational wave astronomy has opened, and with it, a new window onto black holes, their mergers, their environments, and their role in shaping the cosmos. The James Webb Space Telescope has begun providing observations relevant to black hole astrophysics as well. With its extraordinary infrared sensitivity, James Webb is finding active galaxies and quasars at redshifts previously inaccessible, looking back to within the first few 100 million years of the universe. The supermassive black holes being found at these high redshifts are already remarkably massive. Some have masses of hundreds of millions to billions of solar masses just a few 100 million years after the Big Bang. This creates a problem. How did they grow so large, so fast? If they started from stellar mass black hole seeds and grew by accreting gas at the maximum rate allowed by physics, the Eddington limit, they would need to start their growth very early and maintain maximum accretion continuously. Some of the high redshift black holes James Webb is finding don't fit easily into this picture. They're too massive, too early. Alternative formation scenarios are being explored. Direct collapse black holes, formed when an entire massive gas cloud collapses without going through a stellar phase, could produce much more massive seeds than stellar collapse. Dense clusters of stars in the early universe might have produced black holes of intermediate mass that then grew rapidly. The James Webb observations are constraining these scenarios and pushing theoretical models to their limits. The origin of supermassive black holes is one of the important open questions in cosmology. It connects the very early universe, the physics of the first generations of stars and galaxies, to the properties of the largest structures in the universe today. Understanding it will require both observational advances and theoretical progress on the physics of black hole growth. One aspect of the black hole interior that general relativity describes very specifically is the nature of time near the singularity. Outside the event horizon, space-time is curved, but time retains its usual character. It flows forward. Events happen in sequence. Cause precedes effect. Inside the event horizon, as we discussed, the radial direction toward the singularity becomes time-like. As the singularity approaches, tidal forces grow. In the Schwarzschild case, the approach to the singularity is anisotropic. The space-time geometry oscillates chaotically in the final moments. Different directions of space alternately contract and expand in a sequence of oscillations that become faster and faster as the singularity approaches. The behavior is chaotic in the mathematical sense, sensitive to initial conditions, unpredictable in its detailed evolution. This chaotic approach is called mixmaster dynamics, and the term is used seriously in the scientific literature. It describes the general behavior expected near the type of singularity found at the center of a non-rotating black hole. For a rotating black hole, the approach may be less violent, though this is still a subject of research. The tidal forces are far larger than any that could be survived by any known form of matter long before these oscillations begin, but as a description of the mathematical structure of space-time in the final moments before the singularity. It's precise. And it's precisely this mathematical structure that quantum gravity will need to resolve. There's something that cuts to the heart of why black holes matter beyond their intrinsic strangeness. We are organized matter. Everything you are, every atom in your body, every quantum state in your brain, is information encoded in physical form. The laws of physics that govern you are the same laws that govern the interior of a black hole. The same quantum mechanics that describes your chemistry operates inside the event horizon. The same general relativity that tells us how space and time work near the event horizon applies everywhere in the universe. The information paradox is not a distant, abstract puzzle. It's a question about whether the laws that govern you are complete and consistent. If information is truly lost in black hole evaporation, then there's a process in nature where the fundamental laws break down, where quantum mechanics fails. And if quantum mechanics can fail for black holes, it could in principle fail for other systems too. The consistency of physics is not just an aesthetic preference. It's the foundation on which everything we know is built. The question of what happens inside a black hole is a question about whether our description of reality is complete. And answering it will either confirm that it is, or will reveal where the next great gap is. Either way, the answer will be important. Not just for astrophysics, for the foundations of all of physics. Every major revolution in our understanding of the universe has come from precisely the places where the old theory broke down. Newton's mechanics worked perfectly for everything in ordinary experience. But at very high speeds, it gave wrong answers. Einstein's special relativity resolved the contradiction. Classical thermodynamics worked perfectly for ordinary gases and solids. But at the atomic scale, it predicted infinities that didn't exist. Quantum mechanics resolved the contradiction. The standard model of particle physics works perfectly for all particle interactions we've tested, but it doesn't include gravity. And at the Planck scale, gravity and quantum mechanics contradict each other. Quantum gravity will resolve the contradiction, and it will do so using the black hole as its primary test case. Because the black hole is the one place in the universe where both theories are simultaneously required, where gravity is so extreme that general relativity is essential, and where the quantum effects of Hawking radiation and the singularity mean quantum mechanics is equally essential. You cannot understand a black hole using only one theory. You need both. And the fact that they don't currently agree is the problem that the next revolution in physics will solve. Black holes are not just extreme astrophysical objects. They're the arena where the next revolution is going to happen. They're the frontier. The edge of everything we understand and the entry point to everything we don't yet. The interior of a black hole is the universe's most carefully guarded secret, guarded not by any lack of transparency or deliberate concealment, guarded by geometry, by the mathematical structure of space-time itself. You could go inside and find out, but you'd have to stay. And no observer who stayed has ever been able to report back. The information they gathered, the measurements they made, the physics they witnessed in the final moments before the singularity, all of it sealed inside along with them. The universe is not hiding something from us. The universe has built a one-way door, and it has told us, through mathematics as much as can be told about what's on the other side without walking through. We've worked out the geometry of the crossing. We've derived the temperature of the radiation that leaks out. We've mapped the quantum mechanical constraints on what can and can't be lost. We've shown, mathematically, that information is probably preserved. We've demonstrated that general relativity predicts a singularity, and that quantum gravity will replace it with something physical. We've built the mathematical frameworks that will eventually describe the resolution. We just haven't found the complete framework yet. That is what remains. That is what the physicists working on this problem are spending their careers on. Because the answer to what happens inside a black hole is the answer to the question of what physics actually is. At the deepest level, where space-time itself is no longer smooth and continuous, and where the quantum nature of reality cannot be ignored. The universe put the hardest question in the hardest possible place to answer, inside a boundary that nothing can cross outward. And it gave us the mathematics to think about it anyway. That is quite a lot. The next time you look up at a clear night sky and see the center of the galaxy in the direction of Sagittarius, you know now that behind all of that starlight, at the heart of the Milky Way, sits a black hole of 4 million solar masses. Its event horizon 12 million kilometers across. Anything that has ever crossed that boundary is gone from our universe in the observational sense. Sealed by geometry, beyond any measurement we could ever make. And at the center of that sealed region, the mathematics says there is a singularity. A place where the description of reality breaks down. A place where something happens that we don't have the equations to describe yet. A question written into the structure of space-time, waiting for the answer we haven't found. Not because we haven't looked hard enough, because the answer requires a language we're still learning to speak. Physics is learning that language, one paper at a time, one equation at a time, one measurement at a time. And when it does, the inside of a black hole will no longer be the place where physics breaks down. It will be the place where physics, finally, completely, understands itself. We know where the darkness begins. We're learning what it's made of. And one day, the equations will open and show us what's on the other side. Until then, the interior is waiting, patient and silent, certain that the answer exists, just as certain that it won't tell us. Good night.